if it's an improper function, we rewrite it like this, where it's a polynomial plus a proper rational function, because we know that a proper rational function always tends towards 0 in the long run. When it's in the long run, that says x goes to infinity, right? Or negative infinity. How do we know? Why must it be true that a proper rational function always tends towards 0? Because x is huge. Michael? Why? How do you know that a proper rational function, every proper rational function, tends towards 0 in the long run? And it's bigger degree, which means it grows faster. And it's yeah, but this is a long run. Day 3 part of the package. So just to go through the exercise again, if I plug in the thousands, the numerator is what, 3004. The denominator is 2 million. It's making bigger, but it grows even faster though. So if you plug in a million, you get 3,000,004, and you get 2 trillion, which is roughly a million times bigger now. And then if you plug in a billion, the denominator is around a billion times bigger, and a trillion is a trillion times bigger. And so, the denominator is growing faster, so so the whole thing tends towards 0 in the long run. And so listen, let's say this again. This is our function. This whole thing was our function as well, right? But in this form, this part is fading away. It's tending towards 0, which means this part is your asymptote. Once you do the division, you'll get a polynomial, also a proper rational function, and the polynomial part is always your long-run asymptote, either horizontal or oblique, depending whether it's horizontal or oblique. And then this part, you take that ratio of the lead terms, so the numericals on there, and that ratio tells you model, which tells you how it approaches the asymptote. Listen, let me show you one more example. So I said, when you do long division, whenever you get there, will be your asymptote. What if you do long division, you got this? Well, then your asymptote is parabola. That could happen. And just to show you possibilities, let's say there's vertical asymptote through there. Then on this side, actually, if it's approaching like this from above, it's approaching like that here. It's below on the left side. And then kind of a typical case is to go like that in here, and go like that. You get that idea. We won't do a problem like that, but I'm saying the asymptote doesn't even have to be aligned, technically. So whatever polynomial you get here is your asymptote that is approaching. And why is it approaching? Because this part tending towards 0. One more way to help you, like we say the model is 1 over x, and you use that. You could also just say that, like if you plug in a million, this fraction is a positive fraction, isn't it? A very, very small positive number, which means this whole thing, the y value for our function, is slightly more than the y value for the parabola, which is our asymptote. So you know it's above. If you plug in a negative 1 million in this, don't you get a negative fraction? Which tells you your actual y value for your graph is slightly less than the y value in the parabola. So without even memorizing your different models, you can just figure it out by doing that little analysis, plug in a big positive number, plug in a big negative number, and figure out what you get. Okay? All right. Look at the short run. Number 11, the A4 part. I'm going to do 2 problems. And before I forget, you're going to have a quiz tomorrow over basically day 1, 2, and 3. Day 1 and 2 was last week. It was basically graphing form, transformations of the parent functions. And then day 3 was the long-run behavior, just long-run behavior. So that's what would be on tomorrow's quiz. And then Friday will be problems like this. Okay? All right. Look, and find your note sheet. Have that in front of you. Step 1 of the note sheet says to find the whole. And you do it by factoring. So first step, factor it. That's the numerator, factor the denominator. And in this case, the x plus 2's cancel. And so you have a whole at negative 2. A whole known as a removable discontinuity. Now, one thing I want to need to be very clear on is that look, our original function had a hole in it at -2. This simplified equation isn't actually the same thing. It's the exact same graph except it doesn't have a hole. Okay, so we're going to use this for all our calculations. For some reason, it doesn't have a hole. It had a point where the original had a hole. So if you plug in -2 here, in other words, you get -2 minus 2 for the numerator, -2 plus 3, you get down there, you get -4. So the hole is at -4. Put that point on your graph, but actually don't make it a point, make it a hole. We're done with the first step. Second step, what? Intercepts. X-intercept, you just figure out when the numerator equals 0. So when the numerator equals 0, when x is 2. So put a point at 2. And then the y-intercept, you plug in 0 and you get -2/3, yes? And I don't care if you write these as ordered pairs or as just numbers. Just make sure you label them as x-intercept or y-intercept. All right, that was step 2. What's step 3? Okay. And so first figure out vertical asymptotes. This one has 1 at -3. So after canceling any fraction of the denominator, then you give you a vertical asymptote. We won't need this side, although keep this space open right here. Just in case you need. All right, now listen. And once again, I'm explaining how to find the short model. The notes spell this out, so read that if you need to. So what you do once again is take the xi, or the things undefined, and plug it into your function here, everywhere except for that part of the denominator that where it makes it undefined. So keep x plus 3x plus 3 in other words, but plug -3 into here, you get -5. And if you'd had more factors, you'd plug it into all of them except x and 3. And then you simplify this like we've always done. Take the lead coefficient, the lead term, I should say, of the top and bottom, and basically it's -1/x behavior. Okay, the 5 we don't care about, but the fact that it's negative we do. Let me go ahead and put that x-intercept, the vertical asymptote on the graph. And then we just set the model to -1/x. Well, -1/x goes down to -infinity as it approaches the vertical asymptote from the right. And so put an arrow going down. And always put these arrows within 1 unit of the asymptote. And let's write that up first. So as x approaches -3, both of these actually. If we say short run, we're talking about as x approaches some specific x value. We just do from the right, so put a plus sign there. So as you approach -3 from the right hand side, we said the y values, so the function values, are going down to -infinity. Whereas -1/x will go up to +infinity on the left side of the asymptote. So put an arrow going up to +infinity on the left side, and write that up. Put the negative sign here to indicate from the left side. And say that when the y values are going to +infinity, and there. We're done with the short run analysis. And of course, you do that for every vertical asymptote. Step 4, long run analysis. But for this, it's an improper rational function, so we need to do division. Actually, there's 3 ways you can approach this division problem. You can do long division. We could do synthetic. Let's do synthetic. You put -3 there. X minus 2, so you put 1 minus 2, 1 and -2. Put in the 1, multiply, you get -3, and you get -5. That's your remainder, so we're done. And I'll talk about what that means in a second, but that's how synthetic division will work out. There's another kind of little shortcut. It frankly doesn't work in every problem. You can always divide. But in problems like this, it's a nice little approach to watch. What you do, it's going to work out nicely like this as well, is you take your fraction, rewrite write it as two separate fractions. One of them you need to make it match somehow. So I'm just putting x plus 3 there. But what needs to go here so that my two numerators equal the original numerator? And so that's the basic idea. Split the numerator, or rewrite it so the two numerators equal that. And then that's 1 and minus 5 over x plus 3, which is exactly what the division gave us. And plus negative 5 over x plus 3, but there's minus 5 over x plus 3. So you could have done long division, got this result. You could have done net division, gotten this result. Or in this case, you could have taken this approach and gotten the same result. Also, the division always works. All right, so what's the long run asymptote? Y equals what? 1. But once again, we put it in this form where it's a polynomial, plus or minus a proper rational function, because in the long run, the proper rational function tends towards 0. So this part fades away in the long run, leaving this. So the function approaches that. That polynomial is always your asymptote. It's horizontal in this case, because y equals 1 is horizontal. And then you take this ratio, it's negative 1 over x behavior, the model. And so here, let's write that up. As you go to the right, as x increases with that bound, as x goes to positive infinity, the function values are approaching 1. You can always put the asymptote here. From below, because it's negative 1 over x in the model. And then let me draw that. Once you put it within 1 unit, it's an asymptote. In the other direction, it's going to put from above. Except what negative 1 over x does on the other side. Drew it, push from below in that direction, from below in that direction. Now we connect the dots. Actually, I almost forgot. Crossing point. Now, look, we talked about the fact that in the long run, this part tends toward 0, right? But the function will cross the asymptote exactly when the function equals. In other words, when this equals 0, is when you have a crossing point. But this fraction will never equal 0, will it? So there is no crossing point in this one. So just don't forget about the crossing point. I forgot. Operates. So just connect the dots. Move those. Listen, one little thing. Make sure when you're done, that is actually a hole. Just to show you what people do. So I have a hole. That's successful. And they'll draw the graph. And when I grade it, it doesn't look like a hole, so I take out points. So sure it looks right when you're done, okay? Questions about that one? Number 14 then. I'll do that one and then do it. And by the way, I have to say, I've got basically 5 steps we do in a certain order is the best order, I think. But it doesn't really matter which order you do these things. So if you want to sit down and do all this first, and then do the short run, and then do the long run, then be my guest. But here's your 5 steps, and your 5 things: long run, short run, and the 3 kinds of special points: intercepts, holes, and crossing points. What do we start with? In fact, let me label these. That's step 1, that's step 2, that's step 3, that's step 4, and that's step 5. Why do we save the long run for later? Because you need to cancel. Really, you want to cancel first. That's why we find the hole first, because you want to cancel to make everything easier. You don't want to do a lot of algebra to even simplify. Here. The denominator is x plus 3 squared. And so the x plus 3 cancels. So you have a hole at negative 3. Comma. And then it's x minus 1 squared over x plus 3. So you plug in -3 in the numerator, you get -4 squared is 16. When you plug in 0, you get division by 0, don't you? Which means it actually doesn't have a hole at all. It actually has vertical asymptote at -3. So when you're done, all said and done, you still have, it's still undefined at -3, then that's going to be vertical asymptote. It's kind of a different case. All right, now do intercepts. Let's see. When does the numerator equal 0? We'll try and find the x-intercept. When is that true? Well, when x minus 1 is 0. Basically take sort of both sides. Basically you get 1, right? Put that there for your x-intercept. What's the y-intercept? Hayden? Well, you plug in 0. So what do you get? What do you get from the numerator? 1. Positive 1. When you plug in 0. So yeah, positive 1 over 3. And put that on your graph. And listen, crossing points, you could do now, except for one thing. You have to do long division first. Okay. We should just do the crossing points now. I saved it to the end because you need a long division first. You need a long division for long run and crossing points. But then you tend to forget about doing this stuff. So let's get that out of the way. Okay, I need to do long division first. Actually, in this case, I can do some zeta, can I? So I'm dividing by a linear term. So I'll do zeta as well. You do long division if you want. So yeah, some people prefer long division. 3, 5, 15, that's 16. So the whole thing can be written as x minus 5 plus 16 over what? Yeah. So there's our function. So what is the long run asymptote? Again, what's the long run asymptote? Look into this. Yeah. Because remember what I said. We do the division. He gives us a polynomial plus a proper rational function. And what do you know about every proper rational function? In the end, it tends towards 0, which means your function is approaching this part. That is your asymptote, always. And when I say the long run, I say that way because it could be horizontal or oblique. In this case, it's oblique. That's obviously not a horizontal line. But that's always the case. This is always your asymptote, and then this will tell you your model. And that's a positive 1 over x for the model. Now, I need to pause because I was saying I was going to do the crossing points, and I got off track. Let me say it again. In the long run, this proper rational function tends towards 0, so the long run it approaches that line. The crossing point occurs when this part equals 0, because then your function equals the asymptote. So when will this fraction equal 0? Never, because it's on there, on the numerator, it's never equal 0. So in this case, where it says crossing point, put none. And you can put because basically 16 will never equal 0. Once again, read the rule. Step 5 says, figure out when the numerator of the proper rational function equals 0. If that happens, your function will be equal to this asymptote. All right, I kind of got out of order. Let me come back to the long run. I want to go and do the short run. Now, for short run, and that's one thing you need to appreciate is that you have like 3 different versions of your equation here. For short run, you really want to use this one. 3 in, not here, but in the numerator. And the numerator becomes, what, 16 when you plug in the -3? Once again, read step 3. in your notes, but you plug in that value where the vertical asymptote is, the value that's mixed and defined. You plug it in every part of your function except in that part around there where it's going to make it undefined. And then this positive 1 over x for your model. To draw that, what class is it? X equals negative 3. And there's positive 1 over x, and then on the right it's going to go to positive 70, and the left is going to go to negative 70. I want to write these as limit statements now. You can do it either way. So here we say the limit as x approaches negative 3 from the right is infinity, right? Or the positive infinity at the side. So we only have variable class of infinity this side, this state. And then on the other side, there's on the left side of the asymptote, when there's as you approach negative 3 from the left, it went down to negative 30. That's what we do. Okay? Okay. Let's go back and do the long run, and then we'll be ready to graph. Draw that line. X1 5 is negative 5. You can go up 1, right 1, or 1, you go up 2, right 2. Do a good job of drawing your lines. Actually, you can see I need to extend the vertical asymptote further down. To do that, and redraw that arrow we had. So there's our asymptote. Have that obscuring on me. So if it's approaching, if you want to write behavior, then on the right it's going to approach from above. On the left it's going to approach from below. Because once again, that's what our model does. Whenever x approaches that long run asymptote from above on the right and from below on the left. Then we write that up. I'm going to do some limit statements. So the limit as x goes to infinity. But what is it approaching? X minus 5. So weird. And how is it approaching it? From above, yes? So you put a plus on there. And if you go in the other direction, it's approaching the same thing. Always asymptote to get here. The long way. So it's approaching from below in that direction. All right. Last step, we connect the dots. Here, it's just going to connect somehow. Something like that. So that's our system. Here, look at this. One thing I want you to appreciate is the fact that, like, in theory, this could come down and just touch there at 1. It could also go down and cross and then go under and cross back up. Oh, the crossing point would have come with where it crosses the asymptote. So that doesn't help. Look, it will, we know it will just touch. How do we know that? Yeah. I'll get back to that. Look, if it was going to go cross here, come back, wouldn't it have another x-intercept? And it doesn't. It only has one x-intercept, so it doesn't cross. Besides which, like you noted, where did the 1 come from? From the x minus 1 squared. That rule we learned from polynomials still applies. If the factor has a degree 2, the multiplicity 2, then it's going to bounce or touch there. If it had been cubed, then it would cross with inflection at that point. So that rule for the x-intercept still works the same way. All right, and then we're done.